Okay, salam sejahtera and welcome back. So today we will continue with the third subtopic for chapter 2, 2.3, capacitor with dielectric. Okay, parallel plate capacitor. Okay, so parallel plate capacitor is considered a two parallel metallic plates capacitor of equal area A are separated by a distance. Okay, and the space between the plate is a vacuum. Okay, so either it's vacuum or is it air in between the two plates. Okay, so this is the area and both area are separated with the distance d. Okay, with the distance d. Okay, so when the capacitor is charged, okay, meaning that when you on the power supply, okay, plates have charges of equal magnitude. Okay, equal magnitude, but opposite direction. Opposite sign. Okay, either it's positive Q or a negative Q. And then the potential difference V across the plate is produced. Okay, so when we have two plates, if you refer here, the terminal positive here, okay, terminal positive, the plate terminal positive, charge positive will go to plate positive. Okay, if let's say terminal negative, electron will flow from terminal negative and store in a plate negative. Okay, so here is a plate negative. Okay, so positive terminal, it will connect with positive plate, and then negative terminal, electron will store in a negative plate. Okay, so this is what you need to be aware lah. Okay. Okay, since the distance is very small if compared with the area, so the electric field strength E is uniform between the plates. Okay, so similar like chapter 1, okay, when we learn two parallel plate for electric field, okay, so E for parallel plate, okay, is always uniform. Okay, is always constant. Okay, for a parallel plate. So remember, your E is uniform, sama. Okay, is uniform along the two parallel plate. Okay, the capacitance of air-filled parallel plate. Okay, we can write it as, okay, you can calculate. Okay, what is the capacitance? What is the capacitance? Ataupun what is the storage? Okay, so we can use the equation C. Okay, equals to epsilon naught, where epsilon naught is a permittivity of the free space, okay, times the area over D. Okay, so meaning that if your area is large and your distance between the plate is small, meaning that your storage ataupun capacitance of the capacitor will increase. Okay, meaning that the storage will be bigger. Okay, so this is another way for us to calculate the capacitance. Because for the subtopic first one, we also can use C equals to Q over V. Okay, C equals to Q over V. If let's say you know what is the charges stored inside the two plates, and also questions give us the area of the parallel plate, the distance between the parallel plate, so we can use epsilon naught A over D to calculate the capacitance. Okay, so this is another equations for you to calculate the capacitance. Okay, next we continue. Okay, dielectric. So dielectric is the non-conducting, or we can say is isolating material placed between the plates of a capacitor. Okay, just now we learned is between the two plates is air. Okay, but if let's say we insert a dielectric in between the two plates, okay, let's say this is the plates and this is the dielectric. Okay, this is the dielectric. If let's say we insert a dielectric, and dielectric, this dielectric is usually, okay, let's say this is positive, this is negative, and we connect with the battery, positive terminal. Okay, this is negative terminal and it's connect with negative plate. Okay, so if we insert a dielectric, okay, what happens is your capacitance will increase. The capacitance will increase. Okay, so this is thing that you must know. Okay, when we insert an dielectric, okay, when we insert an dielectric, confirm your C will increase. Okay, C will increase. Okay, so we learn. We go in detail. Okay, when an dielectric such as a rubber, glass, okay, a paper, meaning that all these things is isolating material, is non-conducting material, is inserted between the plates of the capacitor, the capacitance will increase, okay, by a factor of epsilon r, okay, which is called the dielectric constant or relative permeability of the material. So if you insert a dielectric, our capacitor, okay, capacitance, we can write as C equals to epsilon naught, epsilon r, A over the distance between the plates. Okay, so distance between the plates. Okay, so we can also write as C equals to epsilon A over D. Okay, where your epsilon here is referred to epsilon naught, epsilon r. Okay, okay. So just now, why is capacitance for air or vacuum? Okay, just now the question said if let's say it's a vacuum or air, our equation we only write epsilon naught A over D. Why? Because epsilon r for air or for vacuum is always equals to 1. Okay, so actually there's a 1 here. So that's why our capacitance for air or for a vacuum is equals to epsilon naught A over D, because epsilon r is always equals to 1 for air or for a vacuum. Okay, so if let's say you insert the dielectric, of course you must times epsilon r. Okay, where epsilon r is depends on the material. Okay, and usually the value is greater than 1. Okay, because 1 is vacuum. Okay, so your epsilon r must equal or is must greater than 1. Okay. Okay, next is the advantages of inserting the dielectric. Okay, apakah kebaikan dia? Okay, so the first one, of course, your C will increase, increase the capacitance. Okay, number 2 is increase the maximum operating voltage. Okay, sometimes your voltage will increase. And C, possible mechanical support between the plates, which allow the plates to be close together without touching. Okay, close together without touching because we insert the dielectric in between them. So meaning that if C equals to epsilon naught epsilon r A over D, if you insert the dielectric without touching, meaning that your D will decrease. So when D decrease, your C will increase. Meaning that if you insert the dielectric, your D can be decreased. The plates can close to each other. So when the plate is close to each other, the distance between the plates reduce and your capacitance will increase. Capacitance increase meaning that your storage become bigger. You can store more charge. Okay, you can store more charge inside the capacitor. Okay, so this is what we want. If let's say the storage is bigger, we can store more charge. Okay, next. Okay, 2.3a, we will go to define dielectric constant. Okay, so dielectric constant, okay, sometimes we call it as epsilon r. Okay, and this value epsilon r, as I mentioned, is always greater than 1. Okay, it's always greater than 1. Okay, epsilon r equals to 1 actually is for air or for vacuum. Okay, for vacuum or for for air. Okay, so dielectric constant epsilon r is defined as a ratio between the capacitance of a given capacitor with space between the plates filled with the dielectric. Okay, so when you fill with the dielectric, we say C, and the capacitance of the same capacitor with the plate of a vacuum. If let's say it's still vacuum, we call it C naught. Okay, so we can write as epsilon r equals to C over C naught. Okay, C over C naught. Okay, so if we write in detail, okay, you can write C is epsilon naught epsilon r because we insert a dielectric. Okay, A over D. And for C naught, we only there's only vacuum. So epsilon R is equals to 1. A over D. So if we cancel epsilon naught we cancel. A we cancel. D we cancel. Okay, so you will get back your epsilon R. Okay, you'll get back your epsilon R. Okay, so this is the meaning of epsilon R is between the C, okay, the electric, and also C with vacuum. Okay, so since C and C naught is farad over farad, so it's actually no unit because it is farad over farad. So we say no unit meaning that it's dimensionless. Okay, it's dimensionless. No unit, no dimension. Okay, D for parallel plate capacitor. Okay, for parallel plate capacitor. Okay, so this is what I did just now. Okay, we can write as C over C naught. Okay, so C we can write as epsilon naught epsilon R or epsilon only, where epsilon in this epsilon here is refers to epsilon R times epsilon naught. Okay, so if we cancel A, D and D we cancel. Finally, we will get our epsilon R equals to epsilon over epsilon naught. Okay, where your epsilon is equals to epsilon R times epsilon naught. Okay, so this is the epsilon without R and without 0. Okay, without naught. Okay, next. We also can derive it. We can also then define as epsilon R equals to Q over V, where this is C. C equals to Q over V, right? Okay, Q over V. Okay, over Q over V naught. Okay, so we can write as epsilon R equals to V naught over V. So finally, we can write in this. Okay, epsilon R equals to V naught over V. Okay, and V equals to ED. Okay, so our DD we cancel. We can also write as E naught over E. Okay, so as a conclusion, from what we derived just now, okay, from what we derived just now, finally, as a conclusion, we can write our epsilon R, okay, the dielectric constant equals to C over C naught, epsilon over epsilon naught. We can write as V naught over V or E naught over E. Okay, or we can also write Q, Q over Q naught. Okay, so you must remember this equation enough. Okay, between epsilon R we can define as C over C naught, epsilon over epsilon naught. Okay, so this is the equations. Okay, this is the equations. And later I will also, okay, this one is meaning that if your capacitance, when you insert the dielectric, your capacitance will increase. Okay, your constant also will increase. But when you insert the dielectric, your voltage will decrease. Okay, your electric potential will decrease. Okay, but your charge will increase. Okay, why charge increase? Because the storage become bigger. Okay, so when you insert the dielectric, your C will increase, the constant will increase, your voltage will decrease, electric field will decrease, and also your charge will increase because storage become bigger. Okay, so this one later we will come back. Okay, we look at the next subtopic. Okay, so you may pause the video if let's say you haven't finished copy. Okay, so this is okay, the process, the effect, if let's say you insert the dielectric. Okay, so the effect of dielectric on the parallel capacitor. Okay, so this is case 1. Okay, case 1. Now later I will teach you another case, case 2. Okay, so now consider a parallel plate capacitor as shown in figure below. Okay, so this is a plate positive, and at the bottom here is a plate negative. Okay, so the electric field is come up from plate positive to plate negative. Plate positive to plate negative. So this is our electric field, where electric field here in parallel plate is always uniform. Okay, so initially the plates are separated by the vacuum, and it's connected with the battery. Okay, given that the charge on the plate is positive Q and negative Q, okay, so if let's say positive terminal, the charge positive will goes to plate positive. Okay, negative terminal, electron will go to the plate negative. Okay, the battery is now removed. Removed meaning that it's disconnected and the charge on the plate remains constant. Okay, so when the question said the battery is disconnected, okay, when the battery is disconnected, remember your Q will constant. Okay, Q will constant, because when the battery disconnected, meaning that your charge inside cannot move, okay, cannot go in or go out, okay, it will remain constant. Okay, next, the electric field between the plates is uniform, as I mentioned just now. Your E, okay, your E will equals is always uniform for a parallel plate, okay, for parallel plate, okay, and has the magnitude of E naught. Okay, meanwhile, the separation is between the plate is D. Okay, so this is just want to inform you the separation is D and the electric field is E naught. Okay, this is initially. Okay, when the dielectric is placed, the electric field between the plates, the molecule of the dielectric tend to become oriented. Okay, so if we refers to, okay, I draw. Okay, initially, this is the two plates. Let's say this is a plate positive. Okay, this is a plate negative. Okay, initially, you please count how many electric field. 1, 2, 3, 4, 5. Okay, so I will draw a two parallel plate. Okay, two parallel plate. So initially there is a 5 electric field line. Yeah, electric field line. Okay, electric field line. Okay, so when we insert the dielectric inside, okay, when we insert the dielectric inside, okay, so dielectric inside there is a positive and negative charge. Positive, negative charge move randomly. It move randomly. Okay, but when it enter to the electric field, what happen is this charge will oriented soon. Okay, where the positive will near to the negative plate, negative will near to the positive plate. Okay, so it will oriented ataupun susun. Okay, so this one negative near to the positive plate, positive will near to the negative plate, negative, positive. Okay, so just now we have 5 electric field line. Now only left how many? We only left 1, 2, and also 3. Why? Because 2 electric field line already cancelled off by the charges. Okay, already cancelled off. Okay, so we continue. So when the dielectric is placed in the electric field between the plates, the molecule in the dielectric tend to become oriented. Maksudnya dia tersusun with their positive, okay, ended pointing to the negative plate. Macam cikgu lukis lah. You punya positive, it will near to the negative plate. Whereas your negative plate will negative charge will near to the positive plate. Okay, so your negative end, it will towards the positively charged plate. Okay, so it will oriented, dia akan susun. Initially, is moved randomly. So the result is a build-up of positive charge on one surface of the dielectric and of negative charge on the other. Okay, maksudnya dia akan susun lah. Okay, if you refer to your book, okay, sila rujuk you punya buku. Okay, if you refer back to your books, okay, if you refer back to your book, okay, okay. So if you see your book, positive charge, it will near to the negative plate. Whereas your negative charge, okay, and that it will near to the positive plate. Okay, so meaning that the electric field line cancel off. Field lines, field of the electric field line already cancel off. So the number of electric field line within the dielectric reduce. Your E will reduce because when you insert the dielectric, the molecule inside the dielectric, it will cancel off. It will oriented and then it will cancel off the electric field line. Okay, because the new electric field strength E is smaller because it's reduced than your E naught. So the potential difference V across the plate also become less because your E reduced. That's why your electric potential across the capacitor also will reduce. Okay, D is constant because D is the distance between the two plates. Okay, so D is constant. So since V is smaller, well, Q is remains unchanged. Why Q remain unchanged? Because the battery already disconnected. Okay, meaning that your charge cannot flow back to the battery, okay, or cannot flow between them. Okay, because it's disconnected, the circuit is not complete. Okay, so since this is constant, V is reduced, so therefore your C will increase. Okay, your C will increase. Okay, so this is case number 1. Okay, case number 1 where the battery is disconnected. Okay, where the battery is disconnected. So as a conclusion, we can write here. Okay, we can write where. Okay, as a conclusion, we can write it as when you insert a dielectric. Okay, your E will reduce. Why E reduce? Because the molecule oriented. Okay, oriented, and then it will cancel off the electric field. So when insert the dielectric, E will reduce. Okay, so E will reduce. So when E reduce, E equals to V over D. Okay, so D is constant. So your E reduce, meaning that your V across the capacitor also will reduce. Okay, and then C equals to Q over V. Okay, so when your V reduce, okay, and your Q is constant because it's disconnected with the battery, so therefore your C will increase. Okay, meaning that when you insert the dielectric, your capacitance, your storage will increase, will become bigger. Okay, so this is case where, case 1, battery is disconnected. Okay, this is the case 1 where the battery is disconnected. Okay, later we will learn case 2 where the battery is still connected. So this is case 1. Okay, case 1 where the battery is disconnected. Okay, so remember when you insert the dielectric, E reduce, V reduce. V reduce, your C will increase as the charge inside the capacitor is constant because it's disconnected with the battery. There's no wire that connect these two plates. So that's why the charge inside, stored inside, still remain unchanged. So this is case number 1. Okay, case number 1. Okay, we go to case 2. Okay, we go to case 2. Okay, case 2. Okay, you can write in your book. Case 2 is just now, this is the positive plate and this is the negative plate. Okay, so initially, let's say we have 5, 1, 2, 3, 4, 5 electric field. Okay, 5 electric field. So when you insert the dielectric inside, okay, when you insert the dielectric, okay, meaning that the molecule inside the dielectric, it will oriented. Okay, positive to negative, negative to positive. Okay, it will oriented, meaning that your electric field line, just now we have 5 lines, now become 3 lines. So E will reduce. Okay, and this one connect with the battery. Okay, so this is terminal positive, terminal negative. Okay. Okay, so when E reduce, meaning that your E equals to V over D. D, of course, is constant. Okay, so when your E reduce, your VC will also reduce. Okay, will also reduce. Okay, but this is the case still connected, okay, with battery. Still connected with the battery. Okay, meaning that the circuit is still complete. Okay, so this is your V source, V naught, and this is your VC. Okay, so initially, when VC equals to 0, and if you connect with the battery, the charge will flow, electron will flow to this direction and charging until full. Okay, charging until full. So when it's charging until full, you insert the dielectric. What happened is E reduce. So when E reduce, your VC again will reduce. Potential difference across the capacitor will reduce. Okay, so this is case 2 where it's still connected with the battery. Okay, so meaning that your VC, okay, is not equals to V source or the V battery. Okay, so what happened? There is a potential, potential difference across, okay, across the VC and also the battery. Okay, so what happened is the battery, because it's still connected, so the battery will continue, okay, because not balanced, right? Okay, not balanced. So because not balanced, there is an equal potential difference. Okay, there's a potential difference across them, so the battery still connected, it will charging back, okay, by, okay, increase the Q, charging back, charging until your VC equals to your V naught. Okay, until your VC equals to V naught. Okay, until VC equals to V naught. So this is the things that you need to know. Okay, I repeat again. Okay, when initially there's no charge inside. So when we on the power supply, the charge will flow until it fully charged. Okay, so until it's fully charged, until your VC equals to V naught. Okay, now when we insert the dielectric, after it is fully charged, okay, what happened is your E will reduce because the line cancel off. The molecule cancel off the electric field line. So when E reduce, VC also reduce. Okay, so since it is still connected with the battery, okay, so your VC at that moment, when you insert the dielectric, your VC is not equal to V naught. Perhaps your VC is reduced. Okay, so there is a potential difference across the battery and also the potential across the capacitor. Okay, so what happened is because it's still connected with the battery, so the battery will continue charging. Okay, will continue charging, will continue supply the charge. Okay, will continue supply the charge. Also, it will continue supply the charge. Okay, so meaning that your Q will increase. Charging until your VC equals to V naught, until there's no potential difference across the capacitor and also the battery. Okay, so therefore our C equals to Q over V. Your V is constant because finally it will go back to the original value. So V is constant. Okay, so now, because the battery just now charging back, right? So your Q is increasing because the battery is supplying the charge. Okay, just supply charge, okay, until it is fully charging by the battery. So at that time, your C also will increase. Okay, so this is case 2. Okay, so you may copy down case 1 and case 2. Okay, so it depends on the questions whether the battery is disconnected or the battery is still connected. Okay, so you can copy down the explanation. Okay, we go back to just now the page 48. Okay, we go back to page 48. Okay. Okay. So this one you must highlight for these two cases. Okay, for these two cases. Okay, so these two cases. Okay, so these two cases actually, okay, V reduce is for case one. Okay, it's for case one. Okay, where case one is when your E is reduced. Okay, so your E equals to V over D. Okay, V over D. You know, okay, is equal to V over D. Okay, so D is constant, meaning that if your E reduce, your V will reduce. This is for case one. Okay, this is for case one. Okay, and because it's disconnected with the battery, so for case one, Q is still constant. Okay, this is for case two. Okay, when Q will increase. Okay, when E is reduced, your E equals to V over D, your V will reduce. Okay, will reduce just for a while only. Okay, just for a while. Sekejap sahaja. Okay, sekejap sahaja. Just for a while, it will reduce. Okay, it will reduce just for a while only. Because after that, because the battery is still connected. So the battery will supply. Okay, akan bekalkan lah. Okay, charge. Okay, until your VC equals to your V naught. Okay, meaning that at the end, your VC will go back to V naught. Okay, will go back to the initial value. Okay, meaning that your V will remain constant. Okay, you will remain back to the initial value. Okay, will remain constant. Okay, because the battery help the capacitor to charging back. Okay, so your C equals to Q over V. So since your V is constant, okay, and the battery is supplied with the Q charging back, so your Q will increase and C will increase. Okay, so this is for case two. Okay, case two where Q is increased. Case one is when V is reduced. Okay, so it depends on case one or case two. Okay, case one or case two. Okay, so okay, maybe you can okay, we can watch one video. Okay, we can watch one video, and then only we go to the okay, again. Okay. So if you refer here, okay, initially the molecule inside the dielectric is randomly, okay, maybe it's not consistent. So when you insert the into the dielectric, okay, so when you insert to the dielectric, what happens is it will uh oriented, okay, it will oriented, okay, meaning that it will cancel off the, okay, it will cancel off the electric field inside, okay, it will cancel off the electric field inside. Okay, so it will arrange in this form. Okay, so we continue. Okay. Okay, so why it will increase the capacitor? Okay, so meaning that if you refer to the electric field, when you insert, okay, it will cancel off. It will cancel off the electric field. Okay, it will cancel off the electric field. Okay, so when it is cancel off the electric field, what happen is your V also will reduce. So when V reduce, your C will increase. Okay, so this is a case where, okay, just now, okay, just now is the case that when the battery is disconnected. Okay, just now is a case that when the battery is disconnected. So when the battery disconnected, your E reduce, V reduce, your C will increase. Okay, so this is the second case. Second case. Okay, second case where we connect with the battery. Okay, with the connect with the battery. But now, still the same. When we insert the electric, what happen is the molecule inside it will oriented. Okay, it will oriented by themselves, and then it will attract. Okay, and then the electric field line inside the capacitor it will reduce. Okay, it will reduce. It will cancel off. Okay, it will cancel off. But since we still connect with the battery, okay, the potential difference across the VC will reduce. Okay, so the electric field line here is reduced. You see, you see reduced, because they already cancel off by the molecule. But what happened is because it's still connected with the battery, okay, it's still connected with the battery, so the battery will give charge, okay, will give extra charge, okay, will give extra charges, or charging back the capacitor until VC equals to V naught. Okay, so that's why your Q is increasing. Okay, your Q is increasing, but your V is still remain the same, because back to the initial value. So when Q increase, meaning that when it's charging back, Q increase, your C also will increase. Okay, your C also will increase. Okay, so this is the dielectric constant. Okay. Okay. So we go back to the example just now. Wait, this one I must stop first. Okay, so this video link maybe later I will send together with the recording. Okay, so you can watch it by yourself. Okay, so we go to example number 7. Example number 7. Okay, a parallel plate. Okay, a parallel plate has the plates of the area. So remember, change it become meter square. And the distance D, okay, also change into meter. The plate are in a vacuum. Okay, vacuum meaning that epsilon R is equals to 1. If the potential difference across, this is your VC, is equals to 20.1 volt. Okay, determine the capacitance of the capacitor. So capacitance of the capacitor, as I mentioned just now, we have two equations. Either you use C equals to Q over V, or you can use C equals to epsilon naught, epsilon R, A over D. Okay, but for these questions, we don't have Q, so we can use epsilon, not epsilon R. Okay, so epsilon naught is a constant value. Okay, epsilon naught is a constant value, so it's always equals to 8.85 times 10 to the power of negative 12. If you don't know, you can refer to the constant list. Area is 280 cm. So change cm, negative 2. Okay, but remember negative 2 cm, right? Okay, cm. So cm, if we square it up, it become negative 4. Okay, because cm, negative 2, another cm, negative 2, so it become negative 4. Okay, epsilon r, of course, is 1. I just now I am not writing, so epsilon 1 is r. Epsilon r is 1 because it's a vacuum. And the distance separations between the two plates is 0.55 millimeter. So millimeter, we convert it into meter. Okay, so if you press calculator, you will get the capacitance is equal to 4.51 times 10 to the power of negative 10 farad. Unit for capacitance is farad. Okay, so next, we want to find the amount of charge stored in each plate. Okay, so as I mentioned just now, C equals to Q over V, or epsilon naught, epsilon R, A over D. So since we have a capacitance, so our Q is equal to CV. Okay, so C just now we found is 4.51 times 10 to the power of negative 10. And VC is 20.1 volt. So finally, charge that can store inside is 9.07 times 10 to the power of negative 9 coulomb. Okay? Okay, you may pause the video if, let's say, you're still calculating. Okay, see, next, electric field strength. Okay, so we know that electric field strength E is equal to V over D. Okay, so your V just now is 20.1, and your D, the separation is 0.55 milli. Okay, milli, negative 3. So finally, your electric field is equal to 3.66 times 10 to the power of 4. Okay, so we use Newton per coulomb, or you can use volt per meter. You need either one. Okay, you can choose. Okay, so this is example number 7. Okay, example number 7. Okay, example number 8. Example number 8 is your homework. So this is your homework. Okay, then later you need to send it to the Google Classroom. So we will proceed to we'll proceed to example number 9. Okay, number 9, a vacuum parallel plate capacitor has plates. Okay, again, this is you need to convert it into this one. You must convert it into meter, and D convert into meter. Okay, V is given 2000. Then the battery is disconnected. Okay, disconnected. Remember when the question say the battery is disconnected. Okay, so the first thing that you need to remember is when battery is disconnected, Q is constant. Okay, so this is the keywords. When the battery is removed, meaning that the charge cannot flow from one, cannot flow in or out. Okay, that moment your Q is constant. And the dielectric sheet of same area is placed between the plate. Okay, So initially, when it's fully charged, after fully charged, the battery is disconnected. After you fully charge, battery will take out. Okay. So if the presence of the dielectric, the potential difference across the plate is reduced to 500 volt. Okay, 500 volt. Initially is 2000 volt initially. Okay, after that, when we insert the dielectric, it will reduce to 500 volt. Why? Okay, because E reduce. Once your E reduce, your V also will reduce as the D is constant. So that's why when you insert the dielectric after fully charged is 2000. When you insert the dielectric, it becomes 500. Dia sudah kurang because of the electric field line, dia sudah cancel off berapa line. Okay, so determine the initial capacitance of the capacitor. So initial before you insert the dielectric. Before you insert. So before you insert is C naught equals to epsilon naught epsilon R A over D. Okay, so why I write epsilon R? Because I just want to let you used to it. Okay, used to it with this equation. And later, of course, epsilon R is equals to 1. Okay, because this is inside the vacuum initially before it insert the dielectric. So your area is 150 cm square. Cm square meaning that -2 now become -4. Okay, and the distance separation is 2 milli. So milli we convert into meter. Okay, so your initial capacitance is equals to 6.63 times 10 to the power of -11 farad. This is initial. Okay, next, the charge on each plate before the dielectric is inserted. Okay, so C equals to Q over V. So meaning that your Q is equals to CV. So your C, of course, before is C naught. So it's 6.63 times 10 to the power of -11. And the voltage initially before insert is 2000. Okay, so therefore we will get 1.33 times 10 to the power of -7 coulomb. You can press the calculator. Okay. Okay, next. Find the capacitance after. So capacitance, C after, we can find it by using, okay, we have two methods. Either it's epsilon naught, epsilon R, A over D, or we can use C equals to Q over V. Okay, so since we don't have the value for the epsilon R, because when you insert the dielectric, you must know the epsilon R. Okay, so this one we don't know. Okay, so that's we use Q over V. So C equals to Q over V. Okay, Q before after still the same. Still equals to 1.33 times 10 to the power of -7. Okay, because Q is remain constant because it already disconnected with the battery. Okay, so we use back the charge before and after is the same. And V before is 2000, but when you insert the dielectric, it becomes 500. So your new capacitance only equals to 2.66 times 10 to the power of -10 farad. Okay, so if you refers to the capacitor, actually is increasing. Okay, every time when you insert the dielectric, capacitance is increased. Initially, it's -11, now become -10, meaning that your capacitance, the storage become bigger. Okay, next we want to find the relative permittivity. Okay, relative permittivity meaning that is epsilon R. Okay, epsilon R. Okay, so this is sorry, is the epsilon. Okay, epsilon R. Okay, or we can say it is a dielectric constant. Okay, because we already used to use this term, dielectric constant. Okay, so epsilon R, we can either use C, okay, C over C naught, okay, or you can use V what is the equation? V naught over V. Okay. So you can use either one. Okay. If let's say you want to use C is 2.666 times 10 to the power of negative 10 over 1.3. Sorry, C not. Okay, sorry, I'm using wrong value. Okay, initially, okay, so you substitute in your C naught. C naught is equals to 6.63 times 10 to the power of negative 11. So you will get answer is 4. Okay, meaning that is greater than 1 is correct lah. Okay, if you get 0 point something, meaning is wrong because your epsilon r, remember your epsilon r must greater than 1. Okay, the dielectric for the dielectric constant must equal greater than 1 because equals to 1 is vacuum or air. Okay, if you want to use V to calculate, okay, V naught over V. V naught initially is 2000 and after that it reduced to 500. Okay, if you want to use V over V naught over V, you will also get 4. Okay, epsilon r is also equals to 4. Okay, so either one. Okay, either one. Of course, you cannot use Q because Q is constant. Okay, for disconnected case, you cannot use Q. Okay, the next one E. The permittivity of the dielectric material. Okay, so this is actually we are referring to the epsilon only. So epsilon equals to epsilon naught, epsilon r. Okay, so epsilon naught is a constant value where it's equals to 8.85 times 10 to the power of negative 12. And your dielectric constant or relative permittivity is equals to 4. So we will get 3.55 times 10 to the power of negative 11. And we use the unit is C, okay, Coulomb square per Newton per meter square. Okay, so this is the unit for the permittivity of the dielectric material. Okay, next we want to find initial before electric field. So E equals to V over D because it's initial. So this is E naught lah. V of course is V naught. V naught is 2000 and initially is 2000 and the separation is 2 milli. So meaning that your electric field initially is 1 times 10 to the power of 6. Okay, so volt per meter, or you can use, okay, you can use Newton per Coulomb also can. Okay, Newton per Coulomb. Next, the electric field after the dielectric is inserted. Okay, the electric field. So we can actually calculate your E, the new E is equals to a new V over D. Okay, so your new V is 500 and then your D is still the same, 2 times 10 to the power of negative 3. Okay, so you will get 2.49 times 10 to the power of 5 volt per meter. Volt per meter. Okay, meaning that after you insert the dielectric, of course, okay, after you insert the dielectric, of course, the electric field line, it will, okay, electric field, it will reduce. Okay, it will reduce. Okay, so initially it's power of 6, now become power of 5 only. E is reduced. The other method, you also can use this one, epsilon r is equals to E over E naught over E. Okay, so we know that when we insert the dielectric, your E will reduce. Okay, so our new E is equals to epsilon r E naught. Okay, so your epsilon r is 4 and your E naught initially before you insert is equals to E naught is equals to E, your E is equals to, okay, sorry, my equation is wrong. Okay, so your E is equals to E naught over epsilon naught. Okay, is equals to E naught over epsilon R. Okay, so your E naught is 1 times 10 to the power of E naught, 6. And then your epsilon R is equals to 4. So finally, we will get 2.5 times 10 to the power of 5 volt per meter as well. Okay, you will get the same answer. Okay, so this is the alternative way. Okay, so remember to do the example number 8. So that's all for today class. Okay, hope you can understand. If you don't understand, you can PM teacher. Okay, thank you class. Bye bye.